one of my little drawbacks for taking high school notes and making it college notes and then going back and forth between them. But so the question here is, what if we took an area bounded between this function y equals the cube root of x equals 8, and the x-axis, and spun that around the x-axis? What would be the volume of the new solid? Now, there's certain things that you could figure out just by knowledge of geometry. Like if I took a horizontal line and spun it around an axis, it would create a cylinder. If you know the formula for volume of a cylinder, you don't need calculus, right? If I took a line that had a non-zero slope, right? So not vertical, not horizontal, right? So some line with a slant to it that went through the origin, spun it around the x-axis, you'd create a cone. If you know the volume of a cone formula, you could figure that one out, right? So there are certain things, like, especially when you're dealing with lines, you figure it out with just basic geometry. Anything else might be a little bit of a different story. Depending on the type of curve, maybe it creates part of a sphere. Maybe it creates, something that's almost spherical, right? In this case, this looks like it could be kind of, sort of, in the neighborhood of half of a sphere, but not quite. So we know that we're not expecting the volume to be just half of the volume of a sphere. Right? So we need another technique. Right? So what we do, and it's very, very simple, but for whatever reason, that didn't stop me from screwing it up the first 17 times I tried it when I was a student. Honestly, I say stuff like that. I didn't really screw it up as much as I just wasn't paying attention during any of the instruction. That's a me problem. That's one of life's things where it's like, yeah, you're like not a good student. Why are you a teacher now? I don't know. I have no idea. I'm sure the explanation was lovely. It's just I wasn't listening when it happened. Right? But if you're listening now, like I wasn't, then you should not have any trouble with this. All right, so y equals the cube root of x. We're going to spin that around the x-axis. I draw a little icon here, a little spinning icon here, just to remind myself where I'm spinning it. Because you're not always going to spin it around the x-axis. You're not always going to spin it around the y-axis. Sometimes you'll spin it around the line x equals 2, or y equals 2 in the next one. Right? So it's nice to keep track of these things. Right? So if you're spinning it around, what's happening is you're taking every point on the curve and actually that single point is getting spun around the curve, the axis of revolution, right? So that path is going to create a circular pattern, right? So basically, what I'm looking for, it's called the disk method for a reason. I'm looking for the volume of a single disk that would be created if I were to take that point and spin it around the axis. And you're like, okay, a disk, how's that going to happen? Well, we go back to those arbitrary rectangles I've been drawing. Well, let's draw an arbitrary rectangle. I'll make it huge. I'll try to make it not terrible, though. All right, so there's my arbitrary rectangle. If I take that rectangle and spin it around the axis, what does that rectangle really represent? There's parts of a circle that are important, the center and the radius. All right, so that's actually going to be the radius of a circle. All right, that circle will have some area, but I also want it to have some thickness. All right, that thickness is in terms of x, so that thickness is dx. All right, so what we're looking for is the volume of a single circular disc. Circular disc. That's what I need. Because if I find one, just like with cross sections, if I find one, all I have to do is integrate all of them together over the interval, and I'll have them all. All right. So they told us to go from x equals 0 to x equals 8. I mean, indirectly. Here's 0. It said cap it all off once you get to 8. All right, so if I have a tiny little rectangle here that I spin around, it's going to have its own radius, much smaller. I could have a rectangle, I'll do a different color. I could have a rectangle here that I spin around. It's going to have its own radius. And before you know it, you're going to have an outer edge to this. But in reality, because I mean, this is how I draw, this is how normal people draw, like the internet. And so this is what that's supposed to look like. Now, honestly, I give myself a lot of credit for learning this. I mean, I must be very, very intelligent. The reason I say this is because this drawing, when I was a student, happened without this. So this wasn't there. This was on a chalkboard. And they're like, oh, you see how that's like if you were to spin it around an axis? And I was like, yeah, sure, because you're really nice. And I don't want to hurt your feelings, so I'm just going to agree with you. But it doesn't. It doesn't look like that. Like, I don't know what you're trying to describe here at all. All right? So I put this here because I don't have a chance in hell of being able to come up with this on my own. But this, I at least have a puncher's chance. All right? But I can do you one better. That's what it's supposed to look like. Well, okay, that's all well and good. We still need to come up with a volume. And you don't have the ability to use GeoGebra on the test. So that's, at least not yet. Like, not yet as in, like, not this year, next year, whatever. So, not like, as in next unit. So, I don't want to get anybody's hopes up. That's what I'm really getting at here. So, this represents the radius. That's a distance from the x-axis to a point in space, also known as y. Ah, we have that. So this will be my radius. Area of a circle. Pi r squared. As it turns out, in order to find the volume using the disk method, all you need is the radius, because area is pi r squared, so pi times cube root of x squared. That's the area of the circle. Now the volume of the disk, the circular disk, is just going to be that with its thickness. So pi times the cube root of x squared dx. If I want all of them, because again, I drew 3 examples, but there are infinitely many of those disks. I want to go from 0 to 8 and integrate every single one of those disks together into one solid. All right, that happens by creating the definite integral, pi r, with the r value being the cube root of x squared, cube root of x squared dx. Pop that in your calculator, get an answer, call it a day. All right. So, disk method, pi r squared. Your only challenge, and it's not an insignificant challenge. Your only challenge is to figure out what the r is. Once you do that, you don't have a problem. All right. So, we're going to take the same figure and spin it around the y-axis. All right, so quick sketch. And in the next little section, we'll talk about how we know the difference between one technique and the next. All right. So I'm spinning it around Y. Here's 8. This is Y equals the cube root of X. What was that? Insignificant. All right. So in the last example, that radius was the distance between your axis of revolution and the curve that you wanted to spin. All right. Well, I want to spin it around the y-axis, so that's my axis of revolution. The curve I want to spin is still the same curve. So my arbitrary rectangle is going to look like this. Its thickness will be dy. Now, I was barely able to make my way through a representative graph associated with the cross sections. The equilateral triangle is the limit of what I was willing to attempt. I can't draw these to save my life. So I'm not going to ask you to draw the three-dimensional surface associated with a disk method, washer method, or cylindrical shell. All right, so you just need to set up your integral and worst case scenario, pop it into your calculator. All right, so again, you're not actually figuring anything out by hand. All right, so just like areas, we're looking for the distance associated with the length of this rectangle. And that's the distance from the y-axis to a point in space. Distance from a y-axis to a point in space is also known as x. All right. If I spin this around the axis, and then back, pretend it's a beautiful looking circle, like some really renowned artist doing it, suspend your disbelief. That x is going to end up being your radius. Just like in the last part, the y was the radius. All right. So I have a relation between x and y. X, I just cubed both sides. X is equal to y cubed. Area of the circle, pi r squared, would be pi times my radius, which is y cubed, squared. Honestly, I can't resist the urge. Pi y to the 6th. If you're unsure, resist the urge, because the number of people who have put pi y to the 5th over the years is more than I'm comfortable with. Your calculator understands order of operations better than we do, so let it do the work. All right, power to a power, you multiply the exponents though. All right, so the volume of your disk is going to be that area, pi y to the 6th, with thickness dy. So if I want all of them, and I do, I'm going to go from 0 to 2, because those are the bounds that were given to me. I did mark 8 on there, though, for some reason. Oh, because that was given in the last part. This is saying go up to 2, to y equals 2. So 0 to 2, pi y to the 6th dy. All right, pop that in your calculator and you'll get your answer. All right, now if you compare that to the answer that you got for the previous one, you should not expect them to be the same, because even though I didn't draw this figure, you can't imagine that spinning the curve around the y-axis is going to produce the same figure as you would get if you spun it around the x-axis. You spin it around the x-axis, you get like whatever that thimble-looking thing was. You spin it around the y-axis, you're going to get something that looks kind of like a tornado, right? Or like a, well, I don't want to get into Calc 3 terms, but you're talking about like a hyperboloid of some kind. It's basically like a cone that bows in on itself, you know, so it's a completely different shape, so why would you expect it to have the same volume? And in fact, if you were presented with two different figures, like you just think back to elementary school, early middle school, in science class, they handed you, you know, you had the graduated cylinder, they hand you a rock, a little rock, and they hand you like a little marble, and then they hand you like a little die. Like three different figures, three different shapes. If you put them all in, measured them all separately, and got the exact same measurements, you'd probably be like, whoa, how did that happen? They're different. Why would they have the same measurements? It's the same idea here. Right? These are volumes. They're different shapes. Why would they have the same values? All right? So be surprised if they do. Doesn't mean you're wrong. Maybe it's coincidental, but they're not. They're generally not going to. All right? And so we have the next example where we have a hat, a figure of a hat, basically. The area bounded between same stuff. But now we're spinning it around the line x equals 8. All right, what would be the volume of this new solid? All right. The key to everything with the disk method is determining what the radius is. It's pi r squared. What's the r? That's the challenge in every case. Now, I am realistic. I was a student once. What happens? You're taking the test, you know it's a disk method question, and you'll know it's a disk method question. I'll explain that later. I mean, I've kind of already explained it, but I'll really explain it later. You know it's got an r in there, and you know the r has something to do with the function, but you don't know what. Just throw something in there. Like, it's a 5-point question. You have an integral, you have bounds, you have a function, a pi, a function, squared, a d something else. There's only so many things you can get wrong, all right? If you even have some part of it right, you're gonna get a fair amount of credit, okay? Because just the pi r squared part of it, that's like the main structure of the formula. You have like 3 out of 5 points already. The other 2 points are just getting the right stuff in the right place, all right? So really what happens when people screw this up, they go y when they should go x. All right, so odds are, like for this last one, odds are you're going 0 to 8 and everything's in terms of x when it should be 0 to 2 and everything's in terms of y. So that's a point deduction. Maybe it's some like variation on, or maybe actually you just put x to the 6th. So you have another point deduction, but after that, you have the majority of the credit. So the one thing you don't ever want to do, because there's no multiple choice. I don't do multiple choice unless I have to. There's some classes, like in high school, I have to do multiple choice. But if I don't have to, I don't do it. I don't believe in multiple choice. I believe in partial credit because you can demonstrate knowledge in some capacity even with a wrong answer. The only way you can't is if you leave it blank. Never leave anything blank. And don't pull a stunt of like, oh, I don't want them to think I'm stupid, so let me erase everything. The only time I'm going to think you're stupid, honestly, is if you erase everything. Because my first thought is going to be like, well, that was stupid. I could have gave you a point or two, right? So, like, don't ever leave anything blank, even if you think it's absurd. And in fact, when you hand it in, listen, I know number 5 is absurd, but you told us not to erase anything. So this is me not erasing anything, right? Just please, do yourself that favor. I can always find a point. The area bounded between this and x equals 8. So we'll start with that. So same story, different chapter. So y equals the cube root of x. And I'll actually draw the x equals 8. So we're spinning it around x equals 8. That's my axis now. Axis of revolution, not x-axis or y-axis. Right? Bounded between the curve the line, and the x-axis. So it's still, it's like the first example. It's still that little triangular region. So that's where that little hat shape is coming from. So I still need a radius. The radius is the distance from the axis of revolution to the curve that's being revolved. So it's this. So if you could just come up with an expression that represents this, you're in good shape. Because I know everything else. I know it's going from 0 to 2. I should put that on the y-axis. And for that, I'm kind of cheating because I knew that from the last example. If I didn't know that piece of information, I know that this is x equals 8. Plug it into your function, solve for the value of y, you get the 2. All right? So I just need to come up with this radius because that's what's getting spun around. All right? The disk method is the old thing that you used to do when you were a kid in elementary school, and maybe even last week. You take the pencil, you put the ruler on the top of it, and then you just spin it around. That's the disk method. All right? Your pencil is the axis of revolution. So you just got to figure out how far out it's going, right? But in terms of x. Now, the distance from the y-axis to a point in space is x. So this distance here is x. So in the last problem, we used x as our radius. Last problem, maybe two problems. Oh, last problem, yeah. And that gave us y cubed. Well, I don't want that. That's the part I don't want. If I use x as my radius, I'd be spinning around the y-axis. All right? I want, on this interval, everything except for the x. Which would be what? I think I heard it. I mean, but I hear what I want to hear all the time, so maybe I didn't hear it. 8 minus x? Indeed it is. All right, the whole distance here is 8. You got x stuff that you don't want. Take the 8 away from the x, the x away from the 8 that you have in total, and you have the part that you do want. All right, so that's my radius. That's great news. My thickness, the thickness is the driving force behind the type of integral that you're using. All right, if you don't account for the thickness, then you find yourself writing an integral that has 8 minus x in it, and you throw a dx on it, and you call it a day. No, dy tells me that everything has to be in terms of y. All right, so my y values go from 0 to 2. Pi r squared dy. I could put the 8 minus x in there, but then I have a contradiction in an argument. All right? I have an x here and a y there. This isn't Calc 3. You can't do that. So I need an expression that swaps out the x for, well, I need to swap the x out for an expression involving y. All right? Same as before, x is equal to y cubed. So 0 to 2, pi 8 minus y cubed quantity squared dy. And that would be your integral. This is one of those topics, same thing with washer method, which we're going to get to in a sec. One of those topics where you take some time to really think about why it works the way it does. It becomes a piece of knowledge that you never have to study. You just get it. It clicks. Right? It's when you start trying to memorize rules, that's when things fall apart. Right? You're taking this and spinning it around the axis. You got to think about why you're doing that, what's happening when you do that, where your rectangles can exist. Right? Draw, if you're not sure, draw as many rectangles as you can. And then just start counting y's. Say, okay, well, the lowest I can get is here. What's my y? 0. The highest I can get is up here. What's my y? Oh, 2. So, well, that's my 0 to 2. All right, my thickness is dy, so I know the heart of my expression has to be in terms of y. It really just is a matter of coming up with this.